In previous videos, we've looked at a range of basic concepts in electronics, including things like Kirchhoff's laws, series and parallel resistors, Ohm's laws, and more besides. But what we're going to try and do is apply those to a more complicated circuit network. So you can see here that we have a DC circuit network that is a bit more complicated than the examples we might have looked at previously. And this network is made up of resistors, and you can see that these resistors are in a more complicated arrangement in that some of them are in parallel and some are series elements. And what we're going to try and do is we're going to try and apply some of the concepts that we've looked at previously to work out, in this instance, what the different voltages and currents are in this circuit. Ideally, what I would like to try and do is work out the current in each of these four resistors. So I've got these resistors marked R1, R2, R3 and R4. And what we're going to try and do is work out I1, I2, I3 and I4, the currents going through each of these resistors. So what I'm going to try and do in this example is use two of the concepts that we've looked at previously. The first of which is parallel resistors, and the second of which is Kirchhoff's current law. So if either of these are unfamiliar to you, it might be worth going back to look at the videos where we've covered these topics, parallel resistors and Kirchhoff's current law. So let's begin by putting some values on this circuit here. We've given the resistors some terms such as R1, R2, R3, R4, and we've called the battery, the voltage supply, Vs. But what we can do is put some specific values on these components. So let's say that the voltage of the battery is 15 volts. So we've got a 15 volt battery there at the top. And let's say that that resistor R1 is 330 ohms. The resistor R2 will now give a value of 220 ohms. The resistor R3 we'll say has a value of 470 ohms. And the resistor R4 has a value of 560 ohms. So what we can do first of all is simplify this circuit, because the way that it's presented at the minute is probably too difficult for us to start working out currents and voltages. We want to make things easier for ourselves by simplifying this circuit as much as possible. And so the first thing we can look to do is to try and simplify this section here where we've got two resistors in parallel. And the way we can do that is by using our parallel resistors formula that we looked at in a previous video. And we said that the formula for working out parallel resistors is 1 over the total, 1 over RT, is equal to 1 over R1 plus 1 over R2. Now, there's an alternative formula that we can use, which is a little bit of a cheat really, but it looks like this. It's RT equals R1 times R2 over R1 plus R2. Now, this formula is a little bit tricky because it's very useful, and it's actually I think it's an easier formula than the previous one, but it only works when we have two resistors. If we have more resistors in parallel, say I had 3 or 4 resistors in parallel, I wouldn't be able to use this formula. I'd have to use the original one. The original one we can extend for as many resistors as we like. But with this second formula here, we can only use it with 2 resistors. But here, I've only got 2 resistors in parallel, so I'm going to use this formula in this instance. So I want to simplify this circuit here, and we can do that by using this second formula. So let's put that into practice, and we can say that RT, in this case I'll probably call it R23. And the reason I'm calling it R23 is because I'm joining R2 and R3 in parallel, and I'm working out the resistance of those two in parallel. So R23 represents R2 and R3 in parallel. So R2, 3, and we'll use our formula here, R1 times R2. Well, in this case, it's R2 times R3. These are our two resistors here. I should probably mark these on, R1, R2, R3, and R4, just so we don't forget. So R2 and R3 in parallel. So we'll scrap that and we'll say that it's going to be R2 and R3. So it's 220 times by 470 over 220 plus 470. And if I work that out, then I get a result of 149.86 ohms, 149.86 ohms. And what I can do now is, looking back at this circuit, I can try and simplify its arrangement. So what I can do is I can pretend, as it were, that rather than having two resistors here of two different values, I'll take those out. Rather than having those two resistors in parallel, what I can now do is I can say, well, I'm pretending that there's just one resistor here with a value of 149.86 ohms. So already I've gone some way to try and simplify this more complicated DC network. We can take another step though, because now I have two resistors in series. So if we have a look at these two resistors, these are a series arrangement of resistors. So what we can do is we can apply the other idea of resistors we looked at in the series and parallel video by saying that these series resistors can be just added together to find a total resistance there. So what I can do now is remove all of those resistors there and replace them with just one resistance in the center there. And what we can do is we can say that I'll call it R1, 2, 3, because it takes into account R1, R2 and R3, is going to be our original resistor on the left hand side, 330, plus the resistance that I'd worked out on the right hand side, 149.86, and that gives me a total of 479.86 ohms. So now I've got a resistor here, 479.86 ohms. So we've gone from having a network of 4 resistors just by using series and parallel resistors. We've simplified this down now to just 2 resistors. And if you look, these 2 resistors are in a parallel arrangement as well. So the last thing I can do is I can simplify both resistances here down to just one resistance, and we can use our parallel formula again. We can say that now, I'll call it RT because it is the total resistance of all of those resistors, is 479.86 in parallel with 560. So using my new formula again, I can say that's 479.86 times 560 over 479.86 plus 560. And if I do that, I get an answer of 258.42 ohms. So the whole network now has a resistance of 258.42 ohms. So what I can do now is I can work out the supply current, because I know the voltage, I know the total resistance of the circuit, so I can work out the supply current IS. So the last step is to say that IS is voltage over resistance. So we can say voltage is 15 divided by this value that we've come up with now for the total resistance, 258.42 ohms. And then what I can do is, if I plug all that into a calculator, I get an answer of 0.058 amps. Or I could better express that by multiplying by a factor of 1,000 as 58 milliamps. So now I know that the supply current coming out of the battery and entering this whole circuit network is 0.058 amps or 58 milliamps. Let's put the rest of those values back in place here. So we said that we had a supply voltage of 15 volts, we had a 330 ohm resistor, a 220 ohm resistor, 470 and 560. So now we know something about our circuit here. We've got our supply voltage of 58 milliamps, which is entering that whole circuit. But when we looked at Kirchhoff's current law, we found that this current will split whenever it reaches a junction. And we've got a couple of instances where there are junctions in this circuit. And we're going to apply Kirchhoff's current law to see how this current splits in this circuit, and then hopefully work out the separate currents that we'll have going through each of our 4 resistors. Well, let's begin by considering the path of the current as it leaves the battery. So we've said that the supply current is 58 milliamps, and we know that the current's going to flow down through the circuit until it reaches this point here. This is our first junction, and the current's then going to split at that point. Some of the current is going to go this way through resistor R1, so we're going to call it I1, and then some of the current is going to go this way through the bottom branch through resistor R4, so we'll call it I4. So we know straight away that that 58 milliamps is going to split into I1 and I4. Now, the path of the current I1, yes, it goes through the resistor R1, but it also goes through this whole network here of resistances before it returns to the source. So what we do is we already know the resistance of this whole network, and so what we can do once again is replace what we have here, this whole resistor network, with just this one resistor that we calculated before our 1, 2 and 3 all combined together. So we can imagine once again that we have just one resistor in place of the 3 there, and we said that that one resistor had a value of 479.86 ohms. So what we have here is 58 milliamps supply current that's going to split, and it's either going to go through the 479.86 ohm resistor there, or it's going to go through the other resistor on the bottom there, R4, which is 560 ohms. So at this point, what we're going to do is we're going to employ our current divider rule, which we covered in a previous video. And if you're not sure about the current divider rule, I would advise going back and having a look at that video. But let's apply it here. So we're going to work out I1 first of all. So we can say that I1 is equal to the supply current, 58 milliamps. So I'll just put 58 here in the formula. I could express this in amps, 0.058 amps, but if I use 58 milliamps, we'll get our answer in milliamps as well. We'll hopefully see that in just a second. So 58 multiplied by a fraction. And what we said in the video is, if we want to work out I1, we'll use the opposite resistance on the top. So in this case, because I1 is going through that top resistor there, we're going to put the bottom resistor on the top of the fraction. So 560 ends up on the top of our fraction there. On the bottom of the fraction, we put both of those resistors added together. 479.86, 479.86 plus the 560. So we use both of those added together on the bottom. And if we calculate that, we get an answer of 31.23 milliamps. 31.23 milliamps. And thinking again of Kirchhoff's current law, which we covered in a previous video as well, we know that I1 and I4 must add up to the supply 58. So what we can do with a little bit of subtraction, we know that whatever remains from 58 must be equal to I4. So we know that the 58 splits into I1, which is 31.23. And so we know that I4 must be whatever remains, which is in this case 26.77 milliamps. Let's at this point return to our original diagram, and we know a few more things now. So first of all, we can say that we know that the supply current, the current coming from the supply, is 58 milliamps. But then we can also now say that I1, the current going through R1, is 31.23 milliamps. And we can say that I4, the current going through R4, was 26.77 milliamps. We still have some more work to do though, because as you can see here, I1, yes, it goes through R1, but it also reaches another junction here, and we'll find that I1 then splits into I2, the current going through R2, and I3, the current going through R3. So again, we're going to use the current divider rule here. So let's set this up once more. We can say that at this junction point here, we can set up a formula for I2 and say that I2 is going to be equal to the current entering that junction, which is I1, so 31.23 multiplied by a fraction. And remember, on the top of that fraction, we must put the opposite resistor to the resistor that the current is going through. So I2 is going through resistor R2, and the opposite resistor is going to be R3. So R3 goes on the top of our fraction, which in this case is 470. And on the bottom of our fraction, both resistors added together, 220 plus 470. And if I calculate that in a calculator, I get an answer of 21.27. Now again, I used milliamps as my supply current, 31.23 milliamps, and so my answer will be in milliamps in this case, 21.27 milliamps. And again, we can use Kirchhoff's current law, because we know that whatever enters a junction must be equal to the sum of the currents leaving that junction. So we know that whatever isn't I2 and what remains must be I3. So I can say that I3 is going to be the difference or the subtraction of I1, 31.23, minus 21.27. Whatever remains must be I3. And so in this case, I3 is 9.96 milliamps. The very last thing we can do in this question is work out the voltage across each of our 4 resistors. And the way we can do that is by using Ohm's law. V equals I times R. Voltage is current times resistance. So what we're going to do is we're going to calculate V1, the voltage across R1, V2, V3, and V4. And we're just going to use Ohm's law to do that, because we know the resistance of each of the resistors, and now we know the current that goes through each of the resistors. So we can set up 4 simple equations. We can say, first of all, V1 is I1, which is 31.23. Now remember, this is 31.23 milliamps, and so if we're going to be correct in our equation, we have to say that that is 31.23 times 10 to the minus 3 amps. Or we could divide by 1,000. That would give us 0.03123. But either way, we must make sure that we're expressing that current in amps if we're going to get the correct answer. So that's the current multiplied by the resistance, which is 330. And likewise, V2, I can say, is the current I2, which we've just worked out as 21.27 times 10 to the minus 3, multiplied by R2, which is 220. V3 is going to be I3, which we said was 9.96, times 10 to the minus 3, multiplied by R3, which was 470. And finally, V4, we'll squeeze out at the bottom there, is I4 26.77 times 10 to the minus 3, multiplied by R4, which is 560. So when we do each of these calculations, we get some interesting results. So first of all, the first one there, 31.23 times 10 to the minus 3 multiplied by 330, I get an answer of 10.31 volts. The second, I get an answer of 4.68 volts. And the third, I also get an answer of 4.68 volts. Now this is interesting because what we see is that parallel resistances actually share the same voltage. So in this case, because these resistors are in parallel, we should always expect to get the same voltage across each one. It's possible to have different currents through each resistor, but the voltages in parallel should always work out the same. And finally, this V4, 26.77 times 10 to the minus 3, multiplied by 560, I get an answer of 15 volts. And this is what we'd expect, really, because you can almost imagine the 560 ohm resistor to be in parallel with the supply, 15 volts there. And what we talked about in the video on Kirchhoff's voltage law was the potential divider rule, that voltages get split when they're in series. But here we just have one resistor that's connected to the 15 volt power supply. And so what we'll expect to see is that the voltage across that resistor will be 15 volts. So we don't even really need to calculate that, but we'll see that if we actually do so and use Ohm's law, we get 15 volts as a result. I hope this video has been useful. We'll look at more examples of DC networks, but what we've done here is we've applied many of the things that we've looked at separately in previous videos, including series and parallel resistors, Kirchhoff's current law and the current divider rule, and finally at the end there, Ohm's law, to really work out exactly what's going on in a more complicated DC network.